Hello all, welcome to this video tutorial on how to model a PV cell using a MATLAB or Simulink. So I'm basically explaining in this video that how to model a single diode model of a PV cell. So this is for only the beginners, the first timers who are trying to model a PV cell, so that it would be of some help. So this is the equivalent circuit. As you already might know that this is the current which is generated by the PV cell, the total current, the photo current, photovoltaic current, and this is the diode which is a representation of the PV cell, the junction, PN junction of the PV cell. So this is a diode current ID, and this is a shunt and series resistances, these two RS and RSH. So these two will be the resistances which are approximated resistances of their body resistance of the PV cell, and this I and V are the terminal voltage and the current. So here these are the basic equations you must know before proceeding for the design of PV cell in MATLAB. So this is the basic building main equation of the current. The total output current I is given by the IPV, the total current supplied by the PV cell, minus this diode current, and also these drops, the current which is the shunt current which is gone, so remaining current will be the I. So this will be the expression for I, and Vt is given by this. So this is the Ns into kT by Q. K is a Boltzmann's constant, T is the temperature, Q is the charge of electron. So IPV is given by this equation, I naught is given by this equation, I naught n which is there is given by this equation. So all these equations you can find in any standard paper on modeling of PV cells. So once you know and understood all these equations, you can start writing these things in the M file. So there, this is the M file, so where in which I have tried to write all these equations. So first I have written all constants, K, the Boltzmann's constant, charge of electron, short circuit current, this is there on the panel, open circuit voltage, K, V, Ki are the voltage constants, and number of series cells connected. This is the operating temperature. You can this is 25 is the nominal, and this is the operating change. You can change it to 35, 40 or 20, 30. You can do it later on. And this is a nominal irradiance. This is the ideality constant of the diode. This is band gap, and this is the operating irradiance. You can change this to 1200 or 800, 600, whatever you want. So these are the series and shunt resistances. These will be available. You have to calculate. They won't be given by the manufacturers. So the equations I've put it in this form, Vtn, and all these equations you can just compare these equations. This I naught n is given by this I naught n is given by Isn by exponential of this. So this is given by this I naught n by this, and I naught is I naught n into t by t and whole cube exponential of this. This is, all these things are given, all these equations I have written here. So these are the things, and this is I vector. I have initialized an array. So and I have initialized with it with a 0. The first element I have made it 0, because as you can see the last this equation. So in this equation everything IPV, I naught, everything we can calculate. The only things we will be left with are V and I. So as you can see, I is there on both right and left hand side, so you have to initialize I with some value, so that for the next values you can use that to calculate. So for doing that, so as we know at open circuit V is 32.9, I will be 0. So for the first time I am doing that by putting this I is 0 and V I am starting from, either you can start it from 32.9.10, or you can start it from the open circuit. If you want, you can start from 32.9 and reduce it by 0.1 and up to 0, so that you can plot the complete VI curve from open circuit to short circuit condition. So this will be open circuit, this will be short circuit, and this will be the I calculation, where I have been IPV minus this equation. You can see this first equation, IPV minus this thing I have calculated separate here. So I will be calculating and storing this. I put 1 and I'll be increasing it, so that in the I vector I'm going to store the values of I. So as well as in the V1 I'm going to store the values of V voltage, and in the power I'm going to calculate V into I of I, so that I will calculate every instant I'm calculating the power here. So I'll be increasing I in order to store the values. So at the end of this loop, the P and V1 vectors will be one value less than the I. So in order to make both equal, so I have added the last term once more again, so that to make it equal. So I've made a transpose here so that we can plot it easily. So I'm plotting here V1 and I. Now you can see if I run this, now this is the VI curve of the PV cell as expected. So this will be the this will be the short circuit condition, this will be the open circuit condition. So there the voltage is 32.9 and here the current is 8.21. So this is what is the VI curve of the PV cell. So now if you want to plot the PV, so you can simply plot, remove this and include this PV. So plot V versus P and C. So this would be the PV curve of the PV cell. So now this maximum power is around 200 watt here, at this around 27-26 volts. So this will the voltage corresponds to maximum power. And so this is how we can generally do by using the mathematical modeling of the PV cell. We can plot VI and the PV curve for the PV cell. So now if you want to convert this to a Simulink model, so you can, there are two ways of doing this. You can write either directly the equations in the Simulink blocks, or you can use a embedded MATLAB function. So there in this function you can write your function inside it. So here instead of putting extra loop inside this math file, so you are going to put the loop outside, so that you are going to calculate the value of this V and I every time. So you will be getting and you will be plotting the XY graph in order to plot the PV and the VI curve. So here for doing that, there is a this repeating sequence just acts like a loop, like just what we have done, the for loop. So similarly, this lookup table is going to give for every value of this, it is going to generate me a value of voltage. So this voltage I am going to give, the current I am going to get anyhow. So this value, this requires some pattern. That's what we have done for the loop value from V voltage from 32.9 to 0.01 in decreasing order up to 0. So that's what we have to give it to this loop, then only it is going to work. So I have to put this voltage, so for the lookup table, so as, oh sorry, so now if you open it, so this is what are the breakpoints 1 to 330. These are the points I have given, and based upon these things it is going to access the values of this. So now if I run it, so it is asking, but you can remove this if you don't, this is not required for us. So now you see, so now you can see that the same VI curve and the PV curve for the same PV cell. Now this thing you can later, if you want, you can connect, use a constant current source, just I have removed. So this constant current source connected this I to this, and now you can, at these two terminals you can start connecting your normal electrical components like resistance, inductance and capacitance, whatever you want. And you have to use a power GUI block whenever you are using this kind of extra arrangement, this kind of electrical elements you are using. This thing, this block is a must. I think you already know this. So this is one way of doing it, and the other way of doing it is directly write the equations in terms of a blocks, in terms of blocks. Everything, the equations I put it in this way so that you can do the simulation. So both ways are same only. So here the same thing, this block represents the PV cell, the current is the same block which we have seen just back. So here I have connected this constant current source, controlled current source. So this thing, I have connected a resistor here, and this diode is an extra diode. This is not the diode which we have seen in the one diode model. Okay, this is different, that is different. So now if you run it, now you can see, so this is the VI curve and this is the PV curve. So it is also giving us the same result just as expected, just we have seen for the different cases. So this is the way we can either simulate or you can mathematically implement. So if you want to check for the different irradiations and different temperatures, use it, increase the temperature and see what you are getting. So see, oh, oh, see, it is just varying, distorting, but it should not. Mm. So similarly you can just change, I mean there may be some errors, you can go through and check for all the cases. So for your future work, so just I'm increasing the radiation and see, let us see. So this is how the power is slightly increased. Previously it was 200, now it is 220. So you can increase or decrease the radiance so that you can get, I'm decreasing the radiance, and see the power is decreased, it is around 160 150 now. So similarly this thing you can do it on any model, you can increase the decrease the radiance and the temperature in all models. So this is how you can actually model or simulate the PV cell. So hope this video helps you in this regard. So thank you for watching.